This is a problem from the 11.5 homework in the Larson and Edwards Calculus with early transcendentals text. So we're given this image, and we're told a little bit about this image and what it represents. But basically, you've got a container, and you know that this side length is 6 inches, this side length is 6 inches, and these side lengths are all 8 inches. And you're also told that this side length is 8 inches as well. And you're asked to find the angle between two adjacent sides. Now the idea is this. I can think of this as part of a plane. So I can think of this as my first plane. I'll call that plane 1. And I can think of this side as my second plane. We'll call that plane 2. And our goal is just to find the angle between those two planes, because if we're finding the angle between those two planes, we're finding the angle between the adjacent sides. Now this is hard because this side is sort of coming out at an angle. If we could actually see this in 3D, we would see the bottom is a square. It's a 6 inch by 6 inch square. The top is a square. It's an 8 inch by 8 inch square. And as we go from the square down here to the square up here, we've got these two planes that are sort of going out. So it's kind of difficult to figure out what the components should be in the X and Y direction to get vectors in each of these planes. But I'm getting a little bit ahead of myself. Okay, so we're trying to find the angle between two adjacent sides, which is finding the angle between two planes. And finding the angle between two planes is the same as finding the angle between their normal vectors. So we just need a normal vector for plane 1 and a normal vector for plane 2. And we can find normal vectors for both of the planes if we can find two vectors in each plane. You can have maybe one vector here and one vector there in plane 1, and then another vector here and that vector there is also in plane 2. And when we have those two vectors in a plane, we can take their cross product, and that will give us a normal vector to that plane. And the same is true over here. So we need to find a couple of vectors in the planes. This is actually pretty hard unless we make some assumptions. And even making some assumptions, it's a little bit difficult to draw. But once we make those assumptions, it's pretty straightforward. All we do is find the cross product of two vectors in this plane to get the normal here. Find the cross product of two vectors in this plane to get the normal of that one. And then we find the angle between the two normal vectors using what we know about dot product. So that's the plan. Now we've got to find the vectors. It's going to help us find vectors if we can imagine this in three-dimensional space. Now I'm going to choose to put that back corner, which I can't see, that corner right there. I'm going to choose that for my origin in three-dimensional space. Now, there may be an easier way to do this. I'm just not familiar with it. There's my x-axis, there's my y-axis, and there's my z-axis. And one assumption that I'm going to make is that this 6 by 6 square is in the xy plane. So we're going to go 6 units in the x direction and 6 units in the y direction. And that's the point. X equals 6, y equals 6, z equals 0, that's right there. And then another assumption that I'm going to make is that the top plane here, now this container doesn't actually have a top, but if it did have a top, it would be right here. I'm going to assume that that top plane is parallel to the plane down here. And I'm also going to assume that this little 6 by 6 square fits inside this and it's completely symmetrical. So if I were to look at this from the top, this is what I would see. I'd have this 8 by 8 inch square. And I'll have a 6 by 6 inch square inside. So this is 6 inches, this is 6 inches. And this is 8 inches, and this is 8 inches. Well, I think we can see that if that's 6 and that's 6 and this is 8 and that's 8, then this little distance here has to be 1 inch. And that little distance over there also has to be 1 inch. And of course, similarly, that's 1 inch and that's 1 inch. Okay, so this is what it looks like from the top. And I'm choosing to put that back corner right there for our base at the origin. Okay, so saying, well, how does this relate to the picture over here? It's a very important question. This is what I would see from the top, and I'm assuming that this is at a constant value for z, so it's in a plane that's parallel to the xy plane. So I don't actually know what that constant value of z is yet, but we'll be able to figure out what it is. So let's imagine that we're projecting this little 6 by 6 inch square up some z0 units so that we're in the plane z equals z0. In order to draw that, I'm going to draw lines that are parallel to the coordinate axes that I've drawn already. So I'm just going to take this line, I'm going to draw a parallel line segment over here. And I'm going to take this line and draw a line segment that's parallel. So if this was just a rectangular box, that would be the back corner of my box. Now I want a line segment here that's parallel to the x-axis. And it doesn't have to be perfect, we're just trying to get a visual on what it is we're doing. I'm going to extend that and that. And we have this. Now this is part of that 8 by 8 inch square at the top, but we're actually going to have a 1 inch perimeter around this little square at the top. Okay, so well, how does that change things? That means that once I'm over here on this plane z equals z0, we're going to end up going 1 inch more this way and 1 inch more this way and 1 inch back that way and 1 inch forward this way. So we're actually going to go out to y equals 7 and x equals 7. And then we're going to go back, oops, back to x equals -1 and y equals -1. And I wish I could draw a better picture for you guys, but this is the best I can do. Okay, at least for right now, it's the best I can do. So we're going to go 1 inch this way and 1 inch back. Basically creating a little perimeter. And that's the top. That's the top of my container. And that is going to meet the bottom of our container like this. Now I know it looks weird because it's not to scale, but that's sort of a visual of what's going on here. This is on the plane z equals z0, and this is in the xy plane. Okay, so I need a couple of vectors in this plane and a couple of vectors in this plane. And I notice right away that one vector that they have in common is this vector right here. So if I can find the coordinates of this vector, and that's going to help us. We also know that that vector is parallel to this one in the back, and that one is 8 inches long. If that one's 8 inches long, that one's going to be 8 inches long as well. So let's see. In plane number 1, I've got two vectors, this vector and this vector. And in plane number 2, I've got two vectors, that one and this one. I'm going to call these vectors u, v, and w. Okay, u and w are really easy to find. So u is just going 6 units in the positive y direction. And it's not going any units in the x direction, it's not going forward or backwards, and it's not going up or down. And so u just points in the positive y direction, and it's 6 units long. So it has component form 0, 6, 0. And w is pointed entirely in the negative x direction. Since it's going backwards and not forwards, that's a negative x value. And it's going 6 units in the negative x direction. It's not going left or right, so it's not going in the y direction at all, and it's not going up or down because it's in the xy plane. So the z component there is 0. Now v is the hardest one to find, but we can find it. Knowing what we know about this, and of course this is all based on the assumption that the top of this container is parallel to the bottom of the container. And there's another assumption, we're assuming some symmetry, that this 6 by 6 inch rectangle would fit inside the 8 by 8 inch rectangle and be completely symmetric. So with that in mind, I can find the coordinates of this point right here. Well, notice we went out 1 unit in the y direction and 1 unit in the, or 1 unit in the y direction and 1 unit in the x direction to get here. So this location, given my choice of origin, is x equals 7, y equals 7, and z equals z naught. And we know that this location is 6, 6, 0. So v is the vector from this point to this point. So if I want component form for v, all I have to do is take the coordinates of this point and the coordinates of this point and subtract. So we'll have 7 minus 6, that's 1. 7 minus 6 is 1. And z naught minus 0 is z naught. But we know that the length of v, that vector, and it doesn't look like it in my picture, but that vector, they're going to be the same. Those two lengths have to be 8 inches. So with that in mind, I can find the value of z naught. We know the length of v is the square root of the sum of the components squared. You just take the components, square them, add them, and take the square root. So we get 2 plus z naught squared. And that has to be equal to the length of v. And they told us the length of v was 8. So you can solve this for z naught now by squaring both sides. Then subtract the 2 from both sides, and then take the square root. And we know that z is positive just from our picture. So z naught is square root of 62. And the vector v is in the first plane and the second plane. Okay, so remember the big picture now. We're trying to find the angle between two adjacent sides, which is equivalent to finding the angle between two adjacent planes, which is equivalent to finding the normal vector of this plane and the normal vector of that plane and finding the angle between those. And if we find that in order to find the normal vector of each plane, we need 2 vectors in each plane. We found them. We've got u and v in plane 1 and v and w in plane 2. You just take the cross product of those 2 vectors and it will be perpendicular to both of these. So it'll be normal to that plane. Okay, so we've got u and v and w. Now we just need normal vectors for plane 1 and plane 2. So one normal vector to plane 1 is given by the cross product of u and v. Remember how this works. You take the components of u, you list those in the second row, and the components of v, you list those in the third. And now we are going to cross out the row and column containing I hat. We're going to look at that 2 by 2, like that little 2 by 2 matrix there. And we'll find its determinant and multiply it by I hat. And then for j hat, we always subtract. Cross out the row and column containing j hat. We're subtracting the 2 by 2 determinant where 0, 0 is in the first row, and 1 and square root of 62 is in the second row. That times j hat. And then we'll have another number times k hat, and that number is given by this 2 by 2 determinant. We've got 0, 6 in the first row, and 1, 1 in the second row. So let's evaluate this. We've got this times this minus 0. So we get 6 root 62. And 0 minus 0 times negative 1 is, of course, 0. And over here, we've got 0 minus 6. So that's the normal vector to the first plane. And the normal vector, or a normal vector for the second plane, is w crossed with v. I'm just saying a normal vector as opposed to the normal vector because we have infinitely many normal vectors to any plane. We can always change the length if we want to. Also flip it. Okay. So we cross out the row and column containing I hat and we see this. Now you can skip this step if you want to. You don't have to show this, but a lot of students really like to. Cross out the row and column containing j hat. And you'll have that. And then cross out the row and column containing k hat. And you'll have negative 6, 0, and 1, 1. Okay. So we have 0 minus 0, which is of course 0. And then over here, you've got negative 6 root 62 minus 0 times negative 1. Negative times negative is going to make that a positive. And then we'll have negative 6 minus 0 times k hat. Okay, so those are our two normal vectors. The angle between the planes is the angle between the normal vectors. And we know that the dot product of two vectors is equal to the length of the first vector times the length of the second vector times the cosine of the angle between them. So the cosine of the angle is the dot product of those two vectors divided by the product of their lengths, the product of their magnitudes. Okay. Well, the dot product is pretty easy. You're just going to multiply component by component and add. We'll have this times 0, which is 0, plus 0 times that, which is 0, plus negative 6 times negative 6, which is positive 36. Divided by the product of these two lengths. Notice that they have the same lengths for their components, they're just in a different order, in different directions. So actually, whatever the length is of this one, the length of this one is going to be the same thing. The length of n1 is the square root of 6 root 62 squared plus 0 squared plus negative 6 squared. Remember what we do, we take the components, we square them and add them and take the square root. Now we could do the arithmetic ourselves, but we don't have to. We're in calculus class. I get 18 root 7 over here. Now if you wanted to, you could choose a different normal vector. You could multiply this whole thing by 1/6 or divide by 6 if you wanted to make it smaller. But that's going to be the same length as the length of n2 because the components of this and the components of that are the same, they're just in a different order. So the length of n1 and n2 are both given by 18 times the square root of 7. So we're going to have 18 times the square root of 7 times 18 times the square root of 7. So you have 36 divided by 18 root 7, oops, quantity squared. So you get 1 over 63, that's the cosine of our angle. The angle is the inverse cosine or arc cosine of 1 over 63, which is the inverse cosine. I'm in degree mode. I believe that's how whoever side is requesting your answer in degrees. And I get approximately 89.1 degrees. Okay, so let's just do a brief overview. We're asked to find the angle between two adjacent sides, which is basically finding the angle between this plane and this plane. In order to find the angle between the two planes, we need to find the normal vectors of both planes, and we can find the normal vectors of both planes by finding a vector in each plane. So we needed a vector u, a vector v, and a vector w. And it just so happened that this vector v, if I used this one, it was in both planes. So it was going to work out really nicely. So once we find the 3 vectors, then we take the cross product of these guys to get the normal to this plane. We take the cross product of these 2 guys to get a normal vector to this plane. And then we use the geometric definition of dot product to find the angle between the 2 normal vectors, which is the same as the angle between the 2 planes. So that's the outline, that's the easy part. Now there are a couple of assumptions that were necessary for us to find these vectors. And one wasn't necessary, but I think it simplified our calculations quite a bit. One unnecessary assumption was to put the origin in that back corner of our container there, and then make this 6 by 6 square come out in the positive xy plane over here. So we made that assumption. You could have put the origin anywhere, but that made everything simpler. Another assumption that we made was that this 8-inch by 8-inch square was in a plane parallel to the xy plane. So we were assuming that this was in the plane given by z equals z naught. And we also assumed that the 6-inch by 6-inch square sat inside that 8-inch by 8-inch square, and it was sitting inside in a completely symmetrical way. So with all of those assumptions in mind, we were able to come up with u and w. Those were pretty easy. And then the vector v. And the vector v was found by first finding that corner, given our assumptions. If this is 6, 6 z naught, this is 7, 7 z naught. And then we found the component form of the vector from 6, 6, 0 to 7, 7 z naught. And we used the fact that the length of v was given to be 8 to find z naught. And then once we had those, then we could go on with our plan. So we've got the 3 vectors. You take the cross product of u and v to get the first normal vector. Take cross product of v and w to get the second normal vector. And then we just use the geometric definition of dot product to find the angle between the 2 normal vectors, which is the same as the angle between the 2 planes. That required finding a couple of lengths and a dot product, and we did. And then we just used the inverse cosine to get our answer.